Hi, my name is Mourjo, and my topic for the day is what flow metrics teaches us about designing resilient systems. I'm a senior software engineer at Booking.com, and I've been building and shipping backend systems for the last 10 years. I have been writing about the topic of resilience for about 5 years now, and today's topic is one of the most subtle lessons that I've learned about resilience and in software engineering in general. Resilience starts with acknowledging the reality that everything fails. In fact, everything fails all the time. We put metrics in place because they help us solve problems. Imagine you're on call and in the middle of the night you get this alert. It says that the latency of a service has increased. The service's Grafana panel says the same story. So at this point, you need to get to the root cause of the problem. You see that there is an increase in the number of requests, so it looks like you're onto something. But the server is returning 200 statuses, and by doing so, it is communicating that everything is okay. But clearly, it is not from the client's perspective. What makes this even more confusing is that there is no increase in the server's processing time. So barring the increase in the client's observation of the latency, everything else seems to be normal. But the whole reason for the server to exist is to provide service to the client. So there is a clear disconnect between the metrics the server is producing and the server's understanding of its value proposition to the business. Software is a means to deliver business value, that is, to serve the client. So how can we bring back the notion of business value to the system? That is the topic of my talk today. Let's start with an analogy. Say we want to build a product represented by this plot. To do that, we break up the problem into a set of tasks. These tasks fall under the scope of different teams. And once we have identified the list of tasks to do, the teams can start working on their tasks. Each team works on their tasks in their scope. Say the red team picks up the red tasks, spends time building it, and then it comes out of the other side as a completed work item. In the end, the assembled product is what the customer wanted. From the left to the right, there is an increase in the business value. Teams work on tasks and completed tasks get assembled to form the final product that the customer wants. And that is where flow metrics comes in. The customer wants the final assembled product and not the individual work items that the teams are focused on doing. Thus, each team needs to do its part, and a single bottleneck will delay the entire assembly process. So until the final assembly happens, all the product specifications, the code written by the teams, everything is only theoretically valuable for the customer. Flow here is the movement of items of potential value to become something concrete for the customer. And flow metrics, in turn, are a measure for flow. Let's look at a single team's work items. So the team picks up some work items, it goes into the engineering process, comes out of the other side as an implementation. That is the software engineering process. Our first flow metric here is WIP, or work in progress. This measures the number of things the team has started working on but not yet completed. It is the number of tasks inside this funnel here. Our second flow metric is age, and it defines the time since an in-progress item was started. It is the time a task spends inside the funnel here. Once the implementation is complete, it comes out of the other side, and the amount of time that has elapsed between when the work item had started and when a work item finishes is called its cycle time, which is our third flow metric. Note that the cycle time is only measured after the completion of the work item. And our last flow metric is throughput. This is the number of items that can be finished by a team per unit time. So, note that we did not talk about the nature of the work, like story points, t-shirt sizes, and what have you. Flow metrics just measures how well we are able to deliver what we are asked to deliver. And because of that, to me, flow metric goes beyond the world of building software. Instead of building software, if we add users on one end and servers on the other, and replace the work items with requests, the fundamental nature of the problem does not change. we should still be able to assess how well our system delivers what it is asked to deliver. Let's now look at how we can apply flow metrics into software systems. In its simplest form, a server serves requests to its users, and it depends on a few systems like a database. Users make requests to the server makes queries to the database returns query results to the server then responds to the client. Simple things. Let's now take a scenario where the user makes more requests than expected. This is like a spike in incoming requests, for example. If the server is not able to process that many requests, there will be more requests on the fly. That is, there will be more WIP or work in progress. Let's trace a single request path. Starting from when the user makes a request, it moves along. Finally, the request is picked up by the server, and by this time, it has already waited a long time, which increases its age. That is our second flow metric. It then proceeds to get served. The database returns the query results, and ultimately, the response reaches the user. It has been quite a long time since the request was made, and this increases the cycle time of the request, which is a third flow metric. Now let's reset the scenario and go back to the original system where everything was okay, everything is optimally working, there is no spike in incoming traffic, everything is okay. Assume now that the database has become sluggish. This is not very uncommon, and you might see this every now and then. Because of that, the database is not able to produce query results at the same rate as it was, and this causes more and more queries to the database to accumulate. Again, we observe that there is an increase in WIP immediately. Note that this time there was no spike in incoming requests, but an internal issue completely unrelated to the world. But we still see an increase in WIP. Additionally, the age of the request will also increase because it just takes longer time for the database to produce results. Ultimately, the database will return the result, but the user will observe an increase in the cycle time and a decrease in throughput because there is one dependency which has become slow. So for systems at scale, whenever there is congestion, that is, there is too much to do with not enough capacity, WIP, age, and cycle time increase. WIP and age are leading indicators, which means that they can be observed on the fly. That is, a request does not need to complete before we can measure these. This is not the same for cycle time, which can only be measured after a request finishes processing. Let's apply our leading indicators to the alerting scenario that we saw at the beginning. To recall, the client was observing a latency increase. We knew that the number of requests had gone up, but the processing time was constant, and the server was quite falsely indicating that everything is okay. Let's take away the rest of the metrics because they were not helping us in finding the root cause anyway. So now let's apply the flow metrics. Starting with age, which is one of our flow metrics, we clearly see that there is an increase that resonates with the impact that was observed by the client. Note that the age is divided into two components, the processing time and the waiting time. Once we acknowledge that there is a wait time component, we see that most of the requests were spending its age just waiting for service. Once the waiting is over, the processing time was constant. We also see that the WIP is increasing during this time. This indicates that there is simply too many requests in the system to process. Therefore, there is a problem of congestion in our system. And the root cause of the alert that we saw in the beginning is that there is this congestion that is building up inside the system. Think of a traffic jam on the way back from work. There are too many cars on the road waiting for the traffic to move. Now let's look at this one car. It has to wait for all the cars in front of it. There is no exit for this car. It is completely stuck. Imagine the anniversary dinner that gets spoiled because the traffic wasn't moving fast enough and you did not reach the restaurant on time. We need to do better in our systems. Just detecting congestion is not good enough. So we must make our systems more resilient to congestion. And we can do that with flow metrics. So our server reported that the age of request was high, and most of that age was spent waiting for service. The red requests here have to wait for the yellows and the greens to finish before any of the server threads even starts processing that request. Let's introduce a limit on the VIP items, and we can do this by limiting the queue size so that there are only a few slots remaining for the request to be waiting for service. We also saw that the age of request was increasing, so let's add an age filter. If a request has spent too long waiting, we can just drop it and not serve that request. Now, because we have a limited queue size and a filter that drops requests like this, we need a gatekeeper of sorts that identifies when this happens. Because we have a limited queue size and a filter that drops requests like this, we need a gatekeeper of sorts that identifies when this happens. The gatekeeper threads don't actually do the request processing. They hand over the request to a worker thread that actually does the processing of the request, call the dependencies, etc. When there is no place in the limited queue or the age filter drops the request, the gatekeeper will respond to the client with an appropriate status like 4 to 9, signifying that there are just too many requests in the system and the system is congested. So what are we aiming to do here by limiting VIP in age? First of all, we want a reasonable quality of service so that the clients never have to wait longer than a certain amount of time. When the server is not able to serve the client, the server acknowledges this and the gatekeeper communicates this effectively to the client with an appropriate status and a response code. Because there is an age filter and a smaller queue size, the server will recover faster because there is only so much space now inside this dotted box for the congestion to happen. Think of a highway with a traffic jam. It takes much longer to clear out that traffic jam than a traffic jam in a smaller alley, for example. Now, let's put the VIP and age limit to the test. What I show here are real examples from a real project on GitHub using Spring Boot. This takes inspiration from real services that I've deployed in production. So let's take the scenario that we saw at the beginning with a sudden increase in traffic. Let's compare it to a server that limits VIP and age. So on the left, we have the original server, and on the right is a server that limits VIP and age. Everything else is the same for both of these servers, including the traffic pattern. The original server in this experiment took up to 2 minutes to respond, while the new server took 6 seconds. 2 minutes versus 6 seconds is a huge improvement. Once the additional load went away, as indicated by the blue dotted lines, the original server took a much longer time to recover, while the new server recovered almost immediately after the spike of the requests went away. The original server was always returning 200s, quite falsely communicating that everything is okay, but the new server detects the congestion and gracefully rejects work with 4 to 9 statuses. Note the yellow bars kind of sit above the green bars, clearly showing that there were some requests which were beyond the server's capacity to respond to. Now, instead of a spike in incoming requests, let's see what happens when there is a degraded dependency, like a database that becomes slow. This time, the time to process a request goes up, but there is no increase in the rate of incoming requests. The original server was unresponsive in this case as well, but the new server, without fail, responds within 7 seconds. Same story with the recovery. The new server recovers much more quickly after the degraded dependency is fixed. The original server again responds falsely with 200 statuses, pretending everything is fine, while the new server rejects work when it knows that it is not able to keep up. Notice this time how the yellow bars kind of eat into the server's capacity because of a slow dependency. So even though the rate of incoming requests is constant, the new server is able to reduce its capacity dynamically when it detects a degraded dependency. So we looked at how a single server can utilize flow metrics, but the story goes beyond a single server. We can achieve end-to-end resilience with flow metrics as well. We see that a single server has age and WIP being measured locally. But most often, we will have a cluster of machines serving requests. As more and more requests come in, the requests will be shared across machines. But just because we have more machines does not mean we have infinite capacity. Soon, even the cluster's capacity may get exhausted. Think of a supermarket where there are multiple checkout counters, but each checkout counter starts seeing a queue build up during rush hour. Similarly, each machine in the cluster will notice the WIP and age increasing locally when congestion builds up globally in the cluster. We can therefore abstract out the individual machines and view the cluster as a whole. Now, even though we are making local measurements on the machines of the cluster, we are not measuring the individual servers' capacities. We are measuring how requests flow through the system, irrespective of how many servers there are. If there are requests that are being served in time, whether there are 100 servers or one, it does not really matter to us. Similarly, if there are 1,000 servers, but the requests are not getting responded to in time, then there is a problem of congestion. And each server will be able to detect it just by looking at how quickly servers are able to clear out requests, depending on how quickly requests arrive and how quickly requests are departing from their local queues. This is the power of local measurements of flow that provide global resilience. And not just the number of machines in a cluster. Flow metrics is independent of many system characteristics like memory, load dependencies, CPU utilization, etc. And this is what makes flow metrics just so robust. In fact, Google Research published a paper in 2023 describing their load balancer used in YouTube, which uses flow metrics for balancing load. It does not balance requests based on CPU load, as is often done in load balancers. Instead, it routes requests to machines based on requests in flight and estimated latency, which is similar to our age metric. Also, TCP, the backbone of the internet for over 30 years now, uses flow metrics to avoid congestion. Upon timeout, TCP reduces the number of in-flight requests. That is, TCP reduces the WIP when age increases. Now, congestion control is bundled into TCP, making it so resilient to network issues that we are still using it today after 30 years. So it bodes well for our servers to also have resilience baked into our systems as an insurance policy. Because failures will happen, and we must accept that, especially at scale. Possibility of failures puts your system at risk of not being able to deliver business value. You wouldn't leave your phone unlocked and vulnerable to attackers, so why should you leave your system vulnerable to a sudden burst of traffic or a slow dependency or a memory leak that just causes your system to grind to a halt? Flow metrics does not depend on system characteristics. It just looks at whether our system is able to deliver what it is asked to deliver. And thus, flow metrics can detect a variety of problems without assuming anything about the system. And not just one service. Having such protection is even more crucial for a microservice-based architecture where one slow service can bring down an entire system of interdependent microservices. Flow metrics not only detects problems in one service, but also prevents these kind of problems from cascading across the system. Fundamentally, with flow metrics, we acknowledge that our system has limits. If our system is reaching its limits, it is an outage. First and foremost, a clear communication to our clients is crucial at this time. We did this with congestion detection and appropriate status codes in responses. With flow metrics, we measured the flow of business value through our systems independent of our system characteristics, which is what makes flow metrics so robust. Lastly, flow metrics are very simple to implement, and there is little overhead in doing so. It is truly an insurance policy that ensures business continuity. To me, it is our fiduciary responsibility as engineers to ensure a consistent flow of business value and limit the radius of problems and failures that might happen. Flow metrics helps us doing just that. All that to say that our system design should be aware of the flow of business value and react to whenever the flow of business value is disrupted. And that is what flow metrics teaches us about designing resilient systems. So thank you for listening. If you have any questions, reach out to me on LinkedIn or on email. Thanks a lot, and I hope to see you live at the conference. Thank you.